We derived the autocorrelation for MA2 and we did 3 different equations, ρ1 minus ρ2, ρ2 minus ρ1, and ρ1 over ρ2 to get conditions as to what those values must be. Just like MA1 for us to even have roots of the coefficients, theta 1, theta 2, and so on. I'll do an example on MA2 coefficient estimation after I do MAQ. Autocorrelation. At the end of last class, I showed you, or we wrote ρ1 for MA1, ρ1, ρ2 for MA2, and we sort of recognize that there is a pattern. That's what we're going to do today. Why did we stop at ρ2? MA1, we stopped at ρ1. MA2, we stopped at ρ2. Why?
Because anything greater than 0.
Anything greater than that, theoretically, is 0. Okay, MAQ. I'm using A as our starting input to pick questions from the appropriate sections that are assigned with the reading assignment. So A is when I wrote that book, I'll put S. So XT is 18 minus all that, and those coefficients, theta 1, theta 2, all the way up to theta q could be any value, as long as they are absolutely summable. Unlike AR, where you need to have decreasing values. There is a practical reason for it, mathematical reason for it, practical reason being, you can't have a 0.8 correlation xt minus 1 and 7.9 correlation at xt minus 11. That doesn't make any sense, right? It should diminish as time goes by. But MA on the other hand doesn't matter because they're all random components, and you might have a very high value, say theta 9, which means at time period or time step 9, you had a significant random component. It's called a shock. It happens. Rho H. That, of course, would have XT would be 80 minus that term, and 80 plus H, minus H. It doesn't matter with AR, but it doesn't make any sense to do it with MA. So minus H. We are going to do the exact same thing that we did last time, distribute. So covariance of 80, 80 minus H. Covariance of 80, comma negative sum j equals 1 to q theta j a sub t minus j minus h minus covariance sum I equals 1 to q theta I a sub t minus I that's that at. And lastly, plus covariance of sum I equals third term starts with 18 minus h. And then our term will be I equals 1 to q theta I a t minus I, comma, there's a minus, another minus, and that is what we will have. All I did is I distributed the terms. So first term would be 80 minus h, followed by 80 and that term, then that term with 80 minus h, and lastly those two sums as we go from there. Can certainly break and do gamma naught or rho naught at the very end. This is columns of page, not rows of page. Brain is going ahead of me as always. We can wait and do it at the very last step, but I'm going to do gamma 0 first. If I put h equals 0, I have covariance 80, comma 80. Next term, covariance 80, comma minus sum j equals 1 to q theta j a sub t minus j minus h becomes 0 and minus plus the variance 80, comma minus I equals 1 to q a sub t minus I, comma 80. And lastly, covariance I equals 1 to q theta I 80 minus I, comma sum I equals j equals 1 to q theta j a sub t minus j. H is 0. The very first term, covariance of 80, comma 80 will be sigma squared A. Erin, you have that look. Did I mess something up?
On the top right, you have minus the sum of just AT minus I. Should there be a theta in here as well?
Yeah. Not such a master's, you'll see it in the first one is sigma squared A. What about the second term? Is there a point when the first random component would somehow match with the second? Is there a value of j that would be here so that 80 and that term matches? Can you think of a j? What is the one value of j that will give you a sub t?
0.
0. But is 0 there? No. So that will become 0. Likewise, what is the one value of I that is going to give us a t?
0.
0. It's not possible. So that term will go away. Minus, if I pull that out, I simply have plus. I can pull the sum out also. I can pull theta I out because it's a constant, theta j out because it's a constant, theta I, theta j, covariance of a sub t minus I, colon a sub t minus j. What are the cases when a sub t minus I and a sub t minus j match up so you get sigma squared a?
I equals j.
I has to equal j. So if I is equal to j, I becomes j, so j becomes I, theta I, covariance of a t minus I, comma a t minus I. Now we know what that is, right? That is sigma squared j. There is a sigma squared a here, sigma squared a there. I'm pulling it out to 1 plus I equals 1 to q theta I times theta I squared. If you go back and look at our derivation for MA1, variance for sigma squared A times 1 plus theta 1 squared. Derivation of MA2, sigma squared A times 1 plus theta 1 squared plus theta 2 squared. Yes? For gamma naught. So this is all you need to know. And by changing the family of Q, depending on the order of your process, they can get gamma naught for each of the MA series, MA1, MA2, and so on. Are we clear? Okay. We need that part. Can I erase this? Now comes the case where we've got to find gamma h, where h cannot be 0. If h cannot be 0, would we get sigma squared a here? Could it happen? No. The only time I'll get sigma squared a there is if h is 0, so the first term is 0. Off to the second. H is some number that is not 0. Do you believe that there would be a j that would match those two time values. H can't be 0, but those two must match. Is that a line? Almost says yes. Huh?
Yeah, I changed my mind.
You changed your mind. There is none, so that's 0. Is there a value here when those two time indices match? I equals H. There is only one. And you may ask, well, can you pick that H arbitrarily? Well, no, you are going to pick H between 1 and Q inclusive. Reason being, moving average, we don't look past Q. So when H equals I, that term would be negative covariance sum I equals 1 to Q, theta I, AT minus I, comma AT minus I equals H. So whether you put it as A sub T minus I or T minus H, doesn't matter. H must equal I. Last case. I have a minus in the first term, minus in the second. If you pull it out of the covariance, you have a positive sign. I can pull the sum out also. We can pull the coefficients out as well. So theta I, theta j, covariance of a sub t minus I, comma a sub t minus j minus h. So gamma sub h would simply become negative theta. H is equal to I, and we are trying to get an expression for gamma h, so it is best that we represent in terms of h, because the covariance varies with respect to h. So I'm going to put h plus sum I equals 1 to q, sum j equals 1 to q, theta I, theta j, covariance a sub t minus I. I'm going to rewrite that t minus j plus h. Where did the negative theta h from? This one. That's it. So I'm pulling theta I out, like h is equal to I, so replacing I by h. Why? Well, we are trying to get the other covariance function, which varies for different values of h. So putting I there wouldn't make any sense at all.
Yeah, gotcha. Shouldn't there be a sigma squared A with it?
Must there? Yes. Can you think of a value for either I, j, both, where that time index and that time index match up? Even
I equals j plus A.
when I equals j plus But notice too much, we end up having sigma squared A. Well, that H, if you rewrite it, I minus J, J minus I. Long time ago, I wrote it over here and I said that is something we will see over and over, and there it is again. Yes.
Doesn't that conflict though with the previous step that we did where H equals I?
These are separate time steps. Right? Here it is t minus I and t minus h. So some time step a sub t minus I with a sub t minus h. This is a sub t minus I, but h, that term gets lagged further in the back. Right? So this one is t minus I, t minus h, you stop. The other term, t minus I, cross this, j steps backwards. So they are different time steps. So that condition applies only for that term. Okay, I don't think we need that anymore. So we can erase. Yes. Well. If I use this condition that I is equal to j plus h, I can write theta j plus h times theta j. The sum that depends on, or that depended on both I and j would reduce to a sum that simply depends on j. And sigma squared a. Gonna change j to I. Well, it doesn't matter, I'm just changing the index. I'm doing so because this would match to the convention that we have up there. So I'm just writing j as I, doesn't matter at all. If you go back and look at M81, Q would be 1. And if H is 1, I have negative theta 1. Yes. Q is 1, so you go from 1 to 1, so I would simply be equal to 1. 1 plus 1 is 2, theta 2 times theta 1. Put that as this for an MA1 model. Certainly. Exactly. For an MA1, Q would be 1 there, and this expression would simply be H plus 1 times theta 1. Well, if you plug in, I guess I'm right here, for MA1, gamma H would be sigma squared A times negative theta H plus theta H plus 1 times theta 1. If h equals 0, we don't have an issue, right? But if h is equal to 1, we have a problem, and that problem would be here, 1 plus 1 is 2, theta 2 times theta 1, and then a 1 module does not have theta 2, so that will become 0, resulting in simply sigma squared A times negative theta 1. Go back to your notes, MA1, when we derived gamma 1 was equal to sigma squared A times negative theta 1. Is it? I hope it is. Yes? Okay. So our condition here is h has to be from 0 to 1. For any value past that, gamma h would be 0. Right, MA2, and then generalize. So for MA2, gamma h would be sigma squared A times minus theta sub h plus I would go from 1 all the way up to 2. So theta h plus 1 times theta 1 plus theta h plus 2 times theta 2. Stop. Y, it's an MA2 model, Q is 2, you don't go past that. If I plug in 0, negative theta sub 0 plus theta 0 plus 1, theta 1 times theta 1 squared. Theta 2 times theta 2 squared. What is the value of theta sub 0? Thetas are the coefficients of a sub 2, right? So what is theta sub 0? 1. Is it 1 or is it minus 1? Based on our definition, that is how we write MA2. So that would be 1, and you're tempted to put 1 there. Well, if you put 1 there, you will get negative 1 plus theta 1 squared plus theta 2 squared. That is going to contradict what we had earlier. Yes. What is gamma naught from earlier? It is sigma squared A times 1 plus theta 1 squared plus theta 2 squared. This might sound weird, but if you go with the same convention of minus theta 1, minus theta 2, that has to be minus something. And you may ask, well, why can't you simply change positive coefficient to a negative coefficient, you can't, because a sub t has a mean of 0, correct? And if a sub t has a mean of 0, when you take the expectation, theoretically, whether you have a +1 or -1, the expectation will be 0, correct? So it really doesn't matter. But for the sake of, consistency, we can say that this expression that we have there has to start at 1. For 0, we already have an expression. H equals 1 comes from this term. So that all means if you look at other textbooks and they write this as a sum, they will write it from j equals 0 to q and negative theta 0, theta 1, theta 2, and so on. So whether you have a minus or plus really doesn't matter. Which is why, since day 1, I think you've got to subtract the mean. If you don't subtract the mean, if you don't make the mean 0, you'll end up with problems. You can always add the mean back to the very last step. Okay. I can erase this one. So we already have an expression for gamma naught. We have one for gamma 1, if the h equals 1, sigma squared a minus theta 1 plus theta 1, theta 2 plus theta 3, theta 2. What happens to that term? 0. There is no theta 3 in an MA2 model, so sigma squared a times negative theta 1 plus theta 1, theta 2. Look at your notes from last time. That is the expression that we had for gamma 1. And onward to gamma 2, sigma squared a times minus theta 2, h is 2, plus sum I equals 1 to 2, so theta 2 plus 1, 3, times theta of 1. When I equals 2, h equals 2, theta 4 times theta 2. What would that be? 0. What would that be? 0. So both of them would go away. Simply have sigma squared a times negative theta 2. If you go back and look at the notes from that side, we have negative theta 2 times sigma squared a. What would happen if I plug in 3?
All the terms in the
every single term there would become 0. Yes? So we have to store up to. So we can start at 0, but we have a separate expression. We don't want to confuse ourselves, even though it makes perfect sense. Because of that negative, we've got to know that theta naught is -1. So for the sake of consistency, I'm not including 0 here. Good. Okay. I've got that expression for MA1, that expression for MA2. If you have to take a guess, what would the domain of gamma H be? Domain simply means a set of all possible values for H, because gamma depends on H. So MA1, H was 1, MA2, 1, 2. Take a guess. MA3,
1 to Q.
1, 2, 3. So for an MAQ model, H can only go up to Q. So that is our expression. There is. I'm going to keep H equals 0 separate. So gamma 0 is sigma squared A times 1 plus some I equals 1 to Q into I squared. Gamma H would equal to that expression, sigma squared A times negative theta H, plus some I equals 1 to Q, theta I plus H times theta I. Restoration being H must be 1, 2, ... up to Q. You've got to stop at Q. What happens for any value bigger than Q?
MA2 0.
And that is the autocovariance function of an MAQ model. So all you've got to know is this. And you can pretty much write it for any MA series, but what I'm about to write is something you should know. Rho H is simply gamma H over gamma naught. I just don't want to write a huge expression. That's an easy computation. We can do that.